In this video, we're going to look at a problem that is a projectile motion problem. It involves a number of different concepts that are helpful for review for our kinematics tests. Here we have a golf ball resting on the ground. It's struck by a golf club and given an initial velocity of 50 meters per second at an angle of 30 degrees above the horizontal. The ball heads toward a fence 12 meters high at the end of the golf course, which is 200 meters away from the point at which the golf ball was struck. Neglect any air resistance that may be acting on the golf ball. Part A asks, calculate the time it takes for the ball to reach the plane of the fence. So basically, how long does it take for the ball to get to that 200-meter distance away? First, we're going to just analyze the component parts of the velocity initially of the ball. And it's important that we remember that these vector components that I've drawn in blue and red, they represent the initial velocity in the y direction of the ball and the initial velocity in the x direction of the ball, respectively. And the that green resultant velocity, that indicates the actual direction and launch velocity of the ball itself. We just use the blue and the red there to indicate the component parts, because we need to analyze two-dimensional motion separately. The x and y components we analyze separately. What's happening in the x or horizontal direction happens as if what's happening in the y isn't happening at all, because what happens in the vertical or y direction has no effect on what happens in the horizontal direction, and vice versa. What happens in the x direction has no effect on what happens in the y direction. So we break this vector that's green, that initial velocity vector in green, we break it down or resolve it into the two component parts, the horizontal and the vertical respectively, or the red and the blue, or the v0 x and the v0 y. That way we can look at them together. Or separate, rather. We can always add them back up together to make that green final velocity arrow again, and we do that using, as we've done in class, the Pythagorean theorem to get the magnitude, and our arc tangent, arc sine, arc cosine, one of our arc trig functions to get the angle or the direction. I've copy-pasted those same arrows, and down below shown that we can make that right-angled triangle with them and show that the values of v0 x, for instance, is the hypotenuse times the cosine of the angle that separates them, because the cosine is the relationship between the adjacent and the hypotenuse. I can also find the value of v0 y, the upright or opposite side of the angle, by showing that the resultant velocity, the hypotenuse v0 times the sine of the angle of separation, is equal to that v0 y, because sine is the relationship between the opposite side and the hypotenuse. It's important that we're able to get those values using those trig functions. So let's start off with our t-chart again. I'm going to write down things that I know. I know in projectile motion my acceleration in the x direction is 0. I know that the acceleration in the y direction is g. I know that my initial velocity in the x direction is 50 times the cosine of 30, for the reasons as mentioned above. My velocity final in the x direction is the same as my velocity initial in the x direction, because the acceleration is 0, so that velocity just stays constant. I can call it vx, v0 x, whatever. It's vx is all that I need to know. Delta x, I know, is given in the problem as 200 meters. That's the change in the horizontal position. Time, I don't know yet. Velocity in the y direction, I know, is 50 sine 30 degrees, as mentioned above in my little vector triangle. And v0 y, the final velocity in the y direction, I do not know. Delta y, the change in the vertical position, I do not know. I just know that there's a fence 12 meters high over there, 200 meters away. I don't know if the ball actually makes it to that height after some amount of time for traveling 200 meters. We don't know what delta y is yet. And again, time is going to be simultaneous, but we don't know what that value is. So part A asks, calculate the time it takes for the ball to reach the plane of the fence. How long does it take to get 200 meters away? Well, I know, because I have 0 acceleration in the x direction, that delta x, my range of 200 meters, is equal to the velocity in the x direction times time. So that's the equation I'm going to use. I'll solve for time. That's what I want to find. So I isolate, and I get delta x over v0 cosine theta, or the displacement in the x direction divided by the velocity in the x direction. 200 meters over 50 times the cosine of 30. I know the cosine of 30 is square root of 3 over 2. So without my calculator, I can do a little quick manipulation of the fraction, and I get 2 times 200 meters over 50 times square root of 3, and I get 400 over 50 square root of 3, which is 8 over square root of 3, which is 4.62 seconds. So that's the amount of time it's going to take for that object to get from its initial spot t0, t0, where v0 is, that very initial launch point, 4.62 seconds for it to travel a horizontal distance of 200 meters, given that we know its initial velocity is in the x direction, is 50 cosine 30, and that velocity is going to stay constant throughout the entire trip of 200 meters. And because we know that displacement, or delta x, is 200, and we know our velocity, we can solve for the time, and there it is, 4.62 seconds. I'll write that into my t-chart as another known value now. As a reminder, unit circle is your friend, and those basic trig or common trig values or ratios are given on the AP exam equation sheet. So things for like 30, 60, 90 triangles, what have you, 45, 30, 45, and 90 degrees. No, 30, 45, and 60 degrees. Those common trig cosine sine values for those and tangent values are given in a little table. So it's nice to know those because you can probably solve it a lot quicker than with your calculator, or just write an exact value like 8 divided by the square root of 3, and you got it. Will the ball hit the fence or pass over it? This is part B. Justify your answer by showing your calculations. So maybe the ball goes like this with that purple dotted trajectory, and it hits the fence right below the 12-meter mark. So maybe it doesn't clear the fence. Or maybe it actually goes like this and just barely makes it over. What's important is that we figure out whether or not its change in vertical position after it's moved horizontally 200 meters, whether its change in vertical position is 12 meters or higher. If it's less than that, it means it hits the fence. If it's more than that, it means it's passing over the fence. So our cue here is that if the ball is to clear the fence, then after traveling 200 meters, which we know takes 4.62 seconds, in that x direction, it must have a delta y, or a change in vertical position, or a height above its initial position of plus 12 meters. That's what we got to find out. So we need an equation with delta y in it. We got delta y equals v naught y t minus 1/2 gt squared, and I'm going to substitute in for my v naught y. I know the value v naught sine theta, again from my vector triangle over there, times t minus 1/2 gt squared. I've already solved or isolated the thing I want to find, delta y, and that means I'm just going to substitute in my actual numerical values now. So I got 50 sine 30 times 4.62 seconds minus 1/2 times 10 meters per second squared. I'm using 10 meters per second squared as my g. Down is negative, times my time squared, 4.62 seconds squared. And I get 115.5 meters minus 106.72 meters. So I got about 8.78 meters there for the positive change in the y position. So it doesn't clear the fence. It needs to be 12 meters or higher, and this is showing me that it's changed in vertical position, given that I know a time of 4.62 seconds to travel the 200 meters horizontally to where that fence is. It gives me a change in vertical position of just under 9 meters, so it's not going to make it. If I use 9.8 meters per second squared instead of 10 for my acceleration due to gravity, then the change in vertical position becomes 10.9 meters. Still not enough to clear the fence, but we can see and should be able to conceptually reason out why this value is a little higher than my 8.78 meter value. If my acceleration due to gravity is slightly less than 10, then the ball should be able to achieve a higher vertical position in that same amount of time because it has a less or a lower downward acceleration. If I use 9.8 meters per second instead of 10, which would be a larger acceleration. This last part C, so that the answer to that one is not clearing the fence. Okay, it did not make it above the 12-meter mark. Part C is asking, on the axis provided, or axes provided, sketch a graph of the vertical velocity Vy of the golf ball versus time t. Label all significant points on each graph. So I'm going to start off, I got a red dot over there on the y-axis where we have an initial velocity. It should be v naught y over there. That's the initial launch velocity in the y direction, so that's 50 sine theta, which is just 50 times 1/2, which is 25 meters per second. So I know that's the velocity in the upward or y direction that the ball is starting with. And I know at some point later it's going to reach its maximum height, and at its max height, vertically speaking, it has a velocity of 0. So that's why I put that red dot on the x-axis where v equals 0, and that's going to be at some time t, I don't know where that is in time. But that is where the velocity is going to be 0, and then it's going to impact the fence at some point, and it doesn't get all the way back down to its initial starting height. So its velocity, it doesn't get all the way back down to a minus 25 meters per second velocity because it impacts the fence at some height around 9 meters high. So it still has 9 more meters vertically down to go before it gets to minus 25 meters per second. So where does it exactly end up in terms of its velocity? Well, to figure that out, I can use my kinematic equations. I have a final velocity in the y direction that's equal to an initial velocity in the y direction minus gt. And again, I'm going to use 10 as my g. And I have 50 sine 30, which is just 50 times 1/2. That's my initial velocity in the y. You can see it on my graph over there. Is 25 meters per second. Minus 10 times 4.62 is minus 46.2. So I have a final y velocity of minus 21.2 meters per second. Think about this. This makes physical sense. It was initially positive. The thing was launched upwards into the air at an angle. Now it's gone over its maximum height, and the ball's coming down, so it has a downward velocity at this point. Its change in position is negative, its velocity is negative, and its acceleration is negative, so it's speeding up and heading in the downward direction, so it's a minus velocity, minus 21.2, and the magnitude of its velocity is not as big as it was when it left the golf club. because it hasn't completed the full up and down portion of its trajectory. If you think about throwing a ball straight up and it's coming right back down into my hand, when it hits my hand it should be going the same speed with which it left my hand. But this golf ball, it's impacted some fence before coming back down to where it was originally launched from. So it hasn't achieved that same magnitude of its velocity as it had when it left the golf club. So it makes sense that it's less than the magnitude of 25 meters per second, and it also makes sense that it's negative, indicating that it's downward. So we can show that on my graph now. Let's say that point right there is minus 21.2 meters per second. Okay, so here at this point I'm going to label is when it reaches the max height. It's right there in the middle. I have some times I can write. I have t0 all the way on the left. I have t final, I know is 4.62 seconds. That's when it reaches that minus 21.2 meters per second. The last t for me to figure out is that t when it gets to its maximum height. And I know, again, I can use my kinematic equations for that because I have v naught final. V is going to be 0 when it reaches its maximum height. Final velocity in the y direction is going to be 0 meters per second when it reaches its maximum height. It stops for an instant before it turns around and starts coming back down towards the ground. So there I have v final equals v naught y minus gt. So we said the final velocity in the y direction will be 0 equals 25 meters per second. That was my initial velocity minus my acceleration due to gravity times time. I solve for t, and I've got 2.5 seconds. So it takes 2.5 seconds for it to reach its maximum height. Later at 4.62 seconds is when it reaches that 200 meter horizontal distance, at which point it's about 9 meters above the ground and hits the fence, and has achieved a minus 21.2 velocity downward in the y direction. Those are all three parts for that problem. Let me just go back to the previous page so you can see what we were looking at before. So we want to be able to, in this problem, we solved numerically. We used our t-chart to organize our values. We were able to find time initially here in part A. We found the time based on a known horizontal displacement and a horizontal velocity. We used our trig values or trig functions to figure out the horizontal and vertical components of the velocity. So we were able to find time given that we knew the range and the horizontal velocity. Then we were able to identify whether the ball was actually going to be above or below the fence height after it had traveled that 200 meters horizontally, and we solved that by looking at the vertical displacement after some time of 4.62 seconds. We found out that vertical displacement was less than 9 meters, and depending on which value for g we used. Either way, it's going to be less than 12 meters, so we concluded that it's not going to make it over the fence. It's not going to return to its original starting point. It's going to hit that fence and stop. Then on the next page, we found out sketched the velocity versus time graph for this physical scenario would be, all of which is good practice for both quantitative and our conceptual reasoning that we expect to see on the AP exam.